Today's talk is computational assumptions in blockchains, and an alternate title could be which world do we live in for Impagliazzo's 5 words. It's not maybe which world, but what would happen if we lived in different kind of complexity theoretic worlds. I would like to thank the organizers for inviting me for this event, and I hope you enjoy the rest of the day and the other events during this week. So, at the beginning, let's talk about some ingredients that we're going to have to understand this talk. And the first one is computational hardness, or hardness in general. And we have, in complexity theory, we have several sets of problems, and we try to create these sets in order to reduce problems to each other so that you don't have to solve problems individually. So if you can understand which kind of set a problem belongs to, then we can easily recognize how we can solve them or whether we can solve them at all. So two of these classes are P and NP. I'll just informally go over them. P is a set of problems that we can solve in polynomial time, and NP is the set of problems that we can efficiently verify the solution in polynomial time. So given a solution, we can verify efficiently in the NP, the bigger set. And P, computing the solution itself is also polynomial. And in this world, whenever something is in P, we say that it's easy. It is not to say that it's very concretely efficient. It can be still very slow to compute, but it's at least solvable in some sense. And for NP, this is for verification. So given a solution, we can efficiently verify them. And this description I made doesn't have to be true, because it is not yet proven that it is proven that P is contained in NP, but it is the contrapositive is not proven yet, and these could actually be the same sets, and this is the biggest problem in computer science, basically. So this is just the description as we know of these two sets. They might differ one day. And the second concept we need to distinguish is worst case and average case hardness, and this is somehow overlooked when you get started in cryptography. So in the previous slide, we discussed about a problem being hard, but there we are talking about worst case hardness. So a hardness, the hardest instance of any problem. So for instance, you're finding a shortest path for a graph, let's say, and you can do it for a very simple graph, and that would be an easy instance of this problem. But the actual value comes from whether you can do it in a very large complicated graph, and can you still compute the shortest path. And this is the worst case hardness. So the hardest instance of the problem that you're describing, can you actually solve that instance? Whereas average case hardness is that even if you randomly sample an instance, you sample a random graph, let's say, and even during that time, it is very hard to solve. And this is the reason why you, for instance, if you did complexity theory before, C in your undergraduate classes, you have satisfiability problem, which is one of the hardest problems in computer science technically, because it basically covers all of NP. But you never see it being used in cryptography because you cannot generate you cannot efficiently generate hard instances of that problem. So when you sample a random satisfiability problem, it is most likely easy and not very hard. And that means that this problem doesn't have average case hardness. And these are not very suitable to be used in crypto. And what you see instead is, for instance, this factorization problem. You see it very commonly in crypto. And it doesn't have any formal proof of being NP hard, for instance, so we don't know its worst case hardness. But practically speaking, assuming that factorization is hard, we can very efficiently generate hard instances. So you just sample 2 different primes of a certain size, you multiply them, and you get a problem instance which is n, and the problem is factoring this number n. So this kind of problems, you can build cryptography out of them, because we don't have to search and look for the actual hard instance. We just randomly pick one problem instance, and it's like already hard. That's what average hardness gives us, and it's like the most valuable thing. So if you can find an average case hard problem, which is like easy to sample the instances, you can like most of the time build cryptography out of it. So this is the distinction between worst case and average case. Lastly, we need like one-way functions to describe, like again, very informally, it's just a function that you can like compute in the forward direction very easily, but it's very hard to invert. So given x, you can compute f of x. If f is a one-way function, you can easily compute this y, but given y, and still knowing f, you cannot find x, or it is hard to find x. So this is the object that we have for one-way functions. So now let's go over the actual 5 roles that Impagliazzo defined. By the way, Russell Impagliazzo is a computer scientist, and he wrote this paper in 95, and none of these like complex theoretic worlds have been like proven yet. So we don't know which one do we live in. So tomorrow we can wake up and we can like realize that we are living in one of these. So, but let's describe these worlds first. So in Algorithmica, P is equal to NP. So hard problems like doesn't exist in this complex theoretic sense. So for every easily solvable instance of given a solution, if we can efficiently verify the solution, we can actually compute that solution as well in polynomial time. This is what we mean by not being hard. In heuristica, hardness exists, so there are hard problems, but average case hardness is hard to come by. So although you know that like hard instances of a problem exist, you need to search through them and like actually find a hard problem. So it is not like the factorization problem I described. And there is Passeland. This is like the worst, and that's why it's called Passeland. So it's a quite pessimistic world. So there, average case hardness exists. So you can easily find like hard problems, but you cannot do anything with them because like one-way functions doesn't exist. And what this implies, like the effect of one-way function, non-existence of one-way functions affects this by not being able to know the solutions of the hard problems that we know. So you can pick a random n, let's say, and you know that it has like a prime factorization, but you don't know what the factors are. So in my example, if you remember, we build n ourselves. So by the time we have the instance, like n, we already know which factors are there, so p and q. So in this case, this wouldn't exist. So we can find a like hard factorization problem, but we wouldn't know what the factors are without one-way functions. Minicrypt is much more optimistic. Here, like average case hardness exists, but one-way functions also exist. So here we can have this like one-way function primitive, and we will discuss what we can do with them in a bit. And in the last one, public key cryptography exists, so we can build everything that we are like currently building today. And this is like the right one is what we would like to believe, the world that we live in. But this like characterization basically has this property that like we don't have a proof of so we were not able to eliminate any of these yet. So again, like tomorrow we can wake up with a good enough proof we could be living in any of these. So this is the like property of these like 5 words. But hopefully, like we live in Cryptomania, I will now motivate why we would like to live in Cryptomania, basically. So most of you are maybe here for blockchains, and I will do like a very simple abstraction of them for their like very basic functionality, which is like chaining blocks and like actually creating the blocks themselves as well. So what we do is like whenever like someone creates this block, they first show that this block is actually like a good block, right? So there's this like proof of work or proof of stake, these kind of like Sybil resistance countermeasures, and this basically lets us see that okay, this block is like somehow valid or good. And then there are blocks, and then there are chaining. So these chains basically say, okay, if I give you a chain, you can actually verify that this is like a correct chain. So there are no like other blocks before this. If I like do the computation of this chain, I should only get back like one single block, so I can go through the original block. So like the main two properties that we see in blockchains are these. So the blocks are actually valid, and we can actually chain them properly. So, and this is the only two properties that we're going to discuss today, and nothing more, hopefully. And now I would like to make it more understandable. I will switch to a different model called brick chain, and the goal here is to not do all these like decentralized finance, etc. It is to build a wall. So we're going to use bricks to build a wall, and that's our functionality. So this is this new primitive, let's say. And it has the same kind of structure. So we need like good enough blocks or bricks, and we need some like adhesive paste to like to paste them together so that we have like a good foundational wall. And these blocks need to be somehow robust. So like when we hit it, it shouldn't like break very easily. And I call this like a brick chain. Of course, they're not like really chain, but they're pasted together. So so the question is now, how do we like build a brick chain, not a blockchain? And we will go back to the blockchains at the end of the talk, because I find it easier to understand. So first goal is finding good bricks. And one of the problems is that if there are a lot of, if these bricks, if these bricks are like very easy to find in the nature, then anyone can like put a brick here and come back to us and say, okay, like I put this brick here, I helped building the wall, can you pay me some money? But since there's like a lot of them, there will be like, and if you're actually paying for everyone who put a block, then there will be like a lot of chaos saying, okay, I put this brick, I put that brick, whatever, and it's very hard to keep track of like who put which brick and how much we should pay to someone. So this is like one of the problems that we need to solve. And we also need to find this like adhesive material that we can like use to actually put those bricks to each other. So this is the problem that we're working on. And let's see how this would translate to these 5 worlds. So algorithmica, you cannot even find a brick that is like actually robust enough to like put somewhere. So whenever you put it, like it just falls apart, let's say. This is like what I meant by P equals MP here. So in the first iteration of this figure, we only talked about like complexity theory. It might have been a bit like abstract. Now we are going to like reiterate through it with this brick example so that maybe it will be more easy to understand. So algorithmica, like very hard to find these like good bricks. In heuristica, these bricks exist, but they're like very rare. So if you just go to the ground, like take some rock, it's probably like not in that shape. It's like most of the time it's like the above. So this is what we mean by like worst case hardness exists. So these kind of blocks exist in the wild, we know that, but we need to search for them. It's like very inconvenient for us to find them to actually build a wall. Then Pestilent, as I said, we do actually have these like bricks. But the problem is anyone can find them very easily, and anyone can like try to build these, and they can come to us, okay, like I put this brick there. Oh, like this wall actually is a good example. So I can use that. So maybe someone put this one here, but like since like these are common, we don't know like how to pay who put this, like pay the worker that put this brick. And that is Pestilent. So like even if you have bricks, you cannot create like business incentives so that like the wall becomes useless somehow, at least in this economy. In Minicrypt, with one-way functions, we actually can create like these kind of puzzles. Okay, so if they compute this like one-way function good enough, we can just say, okay, run this one-way function until you get like a number that is less than some value. And once they do that, we know that at least they run the one-way function enough of times so that they can show that, okay, they put this brick specifically here, which is good. So it is not the case with Pestilent. But still with Minicrypt, we don't have this adhesive material that you put in between bricks, so we can have like good bricks, but we cannot paste them to each other. So without collision-resistant hash functions, this cannot happen. So the bricks would look like this, and they would fall apart easily if you just put enough of them. If they're high, they will just fall down without the paste in between. And that paste comes from collision-resistant hash functions. So if you have a collision-resistant hash function or a collision-resistant one-way function, it doesn't have to be a hash function, then we can actually build the wall. But unfortunately, it is not, one-way functions doesn't imply the existence of collision-resistant hash functions. So most of the hash functions that we use today are collision-resistant, and they're like practical hash functions. But this doesn't mean that we live in minicrypt, because if you were living in minicrypt, we only know that one-way function exists, and one-way functions doesn't imply collision resistance. So because of that, like building this wall is not yet known to be possible in minicrypt, at least with this like pasting operation that I said. And with Cryptomania, you have collision resistance easily. You have all these other primitives, like public key cryptography, etc. So it is not like building the wall. You can like build like a whole castle out of this. So you can build Rami library out of these kind of things, like when we have public key cryptography. And okay, this is enough of like brick chains, let's say. And let's do the same with the like blockchain example now, and I think it will be much more easy after like seeing this example. So it is like kind of less interesting because it's like the only functionalities we get like start in like Pesseland. So algorithmically, it's like even hard to like create these blocks because there's no like such correspondence to like a hard problem, let's say. And in heuristica, again, we need to like spend a lot of time to find these blocks. And in Pesseland, okay, we have average case hardness, so we can like somehow create a block, but we have no way of like getting paid for finding this block, let's say, because we cannot solve this like one-way function puzzle. So as I said, it's this like example of paying someone who put a brick. Someone can create a block, but we don't know which person to pay without at least introducing bias. And with one-way functions, we can actually have like a lot of blocks being proposed, and we can actually like verify who actually like built them, and we can pay them. The problem is we cannot chain them still, because if you don't have collision resistant, you can like have these blocks, but there could be like another block here which also point towards here, and there will be like a collision with the one-way function. So one-way function is not enough to build kind of chaining operation. Lastly, again the same. If we like ask the same question, if there was like collision resistance contained in minicrypt, then we could have actually like built this blockchain structured as we know of. But it's only like the structure, so still there's no like signatures here because like one-way functions doesn't imply signatures. So okay, we can create these blocks, we can chain them, but we cannot still sign anything. So there's no like transaction signing, etc. So even for like this simple structure, we need to be in minicrypt. And but luckily today we believe that we live in Cryptomania, but that's just a belief. As I said, it's not proven. It's just like heuristics and like gut instinct, let's say, from the literature that we currently have. And if we had public key crypto, we basically, as I said, have everything. So you have like ZK zero knowledge proofs, rollups, whatever functionality you can build out of zero knowledge proofs, let's say. You have all of public key cryptography, and hence you have like digital signatures by default, so you can actually sign these transactions. And basically every like kind of technology as you know of, which is like more than just doing this like chaining operation, needs to be like conditioned by the fact that we live in Cryptomania and hence public key cryptography exists. So as I said, this was just like since the first talk, I just wanted to like warm everyone up with like some this examples. This is not like any research or anything. It is just like this introduction of like Impagliazzo's 5 first, which is like a framework from '95, and ask the question, what would happen to like the current blockchain technologies we have if we like wake up tomorrow with one of these like worlds. And that was it for me. Thanks a lot again.